So, sir, we will wait for a couple of minutes for
Yeah,
more people to join. Then we can start.
yeah. It's only 2:26 now. The official time is 2:30, so we
Yeah,
need to wait at least till 2:32.
yeah.
Talking about high-speed trains, we are now looking into minutes and seconds. Yeah, good afternoon, Sachin.
Good afternoon, sir.
How are you? Doing well?
Yes, sir.
Fine. Okay.
Good morning, or good afternoon, sir.
Yeah, good afternoon, all. We are waiting.
So, Isra, is Sri Nagesh sir going to join us today?
I asked, let me confirm. Let me call him.
Yeah.
We'll confirm. Yeah.
Good afternoon, sir.
Hi, sir. Good afternoon.
I think
Yeah,
Sir,
good
you are
afternoon.
on mute.
sir.
Yeah, good
You,
afternoon. Sri
Hi,
Nagesh,
good
how are
afternoon,
you?
all.
sir, you
How
are
are
on
you?
mute. Sri Nagesh, sir, you are on mute. Uh,
Yeah,
we cannot
fine,
hear
sir.
you.
Thank
Yeah.
you, sir, so much.
Yeah,
How
yeah,
about you,
okay.
sir?
Yeah, doing well.
Hi,
Yeah, okay.
hi, sir.
Yeah, hi. Good afternoon.
Everyone.
So, yeah, let us start.
Yeah.
So,
Yes, sir.
So let me give
One
a
minute, sir.
brief. Yeah. Hi everyone. So let me give a brief introduction and then we can start our session for today. So my name is Ankur Kumar. I am one of the PWI members for Bangalore chapter and also a committee member for PWI Bengaluru section. And for today, we are actually having the topic for today's session is high speed signaling and interfacing discipline. So first of all, thank you, Kirtivasan sir, for accepting our invite to attend one of to speak on one of the sessions for PWI. And I also thank C Nagesh sir for who is the chair for PWI Bangalore chapter to join this session. And so. Let me give a small brief about our speaker for the today, Vaidyanathan Kirtivasan sir, who is the rail signaling team leader for UK here at WSP with us. So he has 42 years of experience in railway signaling, along with 25 years on Indian Railways and 17 years in other signaling system, including 16 years he has worked in UK rail signaling and 1 year on Australian signaling practices. So today's session will mostly cover what is signaling and what role does it play in safe train operations, what is high speed signaling and how different is it from the normal signaling systems, and how other interfacing systems and disciplines are managed in high speed signaling systems, and we will see their safety features as well. So this was a small brief about our speaker for the today and about our topic. So Kirtivasan sir, if I have missed anything in your introduction, sir, please feel free to add a few words, and after that you can share your screen and we can start the session. I request everyone else to keep their mics on mute and post their any queries in the chat box. We will take those questions at the end of our session. Okay,
yeah,
thank you.
yeah, thank you, Ankur. I know Sri Nagesh right from Arcadis days. So earlier I was in Arcadis from 2010 to 2020. So I joined in Bangalore office in Hyder and then we changed to Arcadis, and then 2014 to 16 I was in UK. 16 to 20 I was in Hyderabad Arcadis, and I know Sri Nagesh very well. We do speak often. So there is nothing much to introduce. Thank you, Sri Nagesh, for having, first of all, given this opportunity and also learning. Yeah, so it's only an interactive session. You can ask your questions. You may have your doubts. You may think all this I am aware about. Then if you are aware, then it's more comfortable. If you are not aware, then this will be a bit new for you. So let me start. Before I start, I just want to give you an introduction about high speed signaling. What do you understand by high speed? So when you say high speed, even if you are going on a cycle, 10 kilometers per hour is high speed. If you are going in your two-wheeler, 30, 40, 50, 60, 70 is high speed. If you are going on a four-wheeler, maybe 120 and 160 is high speed. So what is high speed and what are the problems in high speed train operations? And particularly with regard to signaling and particularly with regard to track and electrical. So these are the three major disciplines that we are going to have a look into it. So I have made a presentation, a few slides. So let me just start sharing it. Yeah. Right. Hope you are able to see the screen.
Yep.
Yes, sir.
Right.
Yes.
Okay. Yeah. So this is what is the start for the day. High speed signaling and interfacing disciplines overview. Now, what is high speed? High speed rail, everyone wants to reach their destination faster. So railway traffic, which was earlier at a slow speed of 30, 40, 50, 60 and all that, now a lot of countries have now gone into the phase of high speed. They want to reach a destination early. Around the world, proposals for new high speed lines are booming. Many existing railway systems are experiencing ever increasing passenger and freight traffic. A lot of passengers wants to move and everybody wants to move very quickly. And some routes are showing signs of stress, such as poor punctuality and overcrowding, often due to capacity constraints of their system. So, this is leading to calls in various countries for new high speed routes to be built to provide more railway capacity with the added benefits of reduction in the pollution and congestion caused by cars on the roads and planes in the sky. So, earlier, if you want to travel fast, normally what you do, you have to travel by flight. You reach the airport and you reach your destination by 1 hour or 2 hours or 3 hours, and including the time that you travel to the airport and wait at the airport for customer clearances and then come out of the other airport and then reach your home, it's almost 6 to 8 hours even for a 1 hour journey, and it's costly also. So if you have faster trains which will take you from your destination to that point within 4 hours or 5 hours, then it becomes more convenient. So that is the reason why a lot of European countries where the distances are small, they have gone in for faster means of transport, not only to capture the air traffic, but also to ensure that a lot of people travel and they reach a destination faster and safer rather than going to the airport and spending more money. Okay, right. So this is about high speed lines. With high speed operation, a safe perception of trackside signals. So when you are going on with high speed trains, the trackside signals, whichever is there, whatever was there for conventional signaling, 100 kilometers or 120 kilometer, you will not be able to see those signals when you're traveling at high speed, because you travel the signal at so high speed that by the time you are able to pick up its aspect, the aspect would have disappeared and you would have forgotten what aspect you have seen. So with high speed operation, a safe perception of the trackside signals by the driver cannot be assumed due to short time which is available for observing the signal. So even in your road traffic also, when you're moving very fast, sometimes you'll miss a road traffic signal because in your speed, you have not observed what that signal was showing. Therefore, railways which use high speeds have defined a limit of speed above which cab signals are obligatory to replace a trackside signal. So what it says is, so different railways have got different practices. So if the speed is more, then they say that no, we will not be providing track signals or trackside signals. We'll be going in for cab signaling. So according to UIC code 734, railway lines can be divided into three classes according to speed and the related form of signalization. One is conventional lines up to about 160 km per hour. Signaling by trackside is possible. Lines with speed up to 200 kilometers. Trackside signals are still possible, but adaptations are necessary so that the signals are clearly visible and all. And high speed lines over 200 kilometers per hour, only cab signaling is possible. So different countries have got different specification for what is high speed lines or high speed signaling. But anything more than 200 kilometers per hour, you need to forget our trackside signals. So people like me who are more experienced in the conventional rail signaling with relay interlocking and HR and DR and all that, they will all have to forget, and they will have to go to communication signaling so that the driver is the signaling is given in the form of communication right in the cab, and the driver is able to safely operate the train. So in a few years, relay interlocking will disappear, cables will disappear, and everything will be on communication based. ETCS, ERTMS, whatever it is. Okay, right. So speed restrictions connected with movements of sites. So these are for different countries. Usually it is between 15 to 30 km per hour, but in special cases can reach 100 kilometers in open line sections in Saudi. Now signals whatever we call it as signals, they can be classified under different criteria. One is the human sense triggered by the signal. The practically important kinds are optical signals. Now, whatever we are using conventional signals, those are optical signals. We call them as optical signal because what it gives is it gives only the light. It doesn't give any other information. It gives only the light. So it depends on the driver to interpret the light correctly and react to that light, whatever it is. Yellow, slow speed; green, full speed; red, stop; double yellow, go with caution. Maybe a lot of other flashing yellow in UK, double green in Germany. So like that, they have got different aspects. But what it gives is only optical. It doesn't tell the driver anything. It only gives an optical information, and the driver will have to use his own brain senses and acknowledge and react accordingly. Second one is audible signals. Audible signals are suitable to attract a person's attention independently so that they are suitable to warn of potentially dangerous situation. Now, audible signals can be any failure on the panel, or it can be a level crossing gate alarm, whatever it is. So audible. So either it is can be heard by the human ear, audible. It can be a buzzer, it can be an alarm, or it can be a sounder, whatever it is. And the second criteria is the location of the signal. Track side signals are given from a position along the track. Vehicle signals are given from vehicles to person outside the vehicle. And cab signals are given in the driver's cab to the driver. Now just let me hope you are able to see the screen. Yeah. So this is the trackside signal where the driver of the train is able to see the trackside signal. This is vehicle signal. So the driver is getting a information that there is a vehicle ahead or whatever it is. And this is your cab signal. So this is how the driver is informed about how he should be controlling his train movement. Is it clear? Any doubts so far? No. Right. So now we are going to discuss some aspects of HS2 in UK, which is already a program which was in progress, but now it has been stopped due to budget constraint or whatever it is. Railways are a high investment system. In the UK, a new double track railway like HS2, it will cost around 76 million per kilometer. Whatever pound, 76 million pounds per kilometer. A modern train will use up to 1.5 million per vehicle. So that is how costly it is going to be to build a faster train or to build a track, a new double track. So an up track and a down track, it is going to cost 76 million per kilometer. Signaling systems will be up to 3 million a kilometer. And power supply and communication also fall in similar price range. So these systems represent a significant investment. That's why it's very costly. Now you see in India, they are talking about bullet trains for the past 4 years. It is going to be very costly because none of the existing infrastructure will match if you're talking about bullet trains. None of the existing infrastructure will match, including track, signaling, nothing will match. Even the coaches also, everything will have to be new, everything will have to be built, and everything will have to be interfaced correctly. So it is going to be a very huge investment. And that's why maybe UK has also stopped it to say that we don't have money now much to invest. For this reason, railways and its system must be planned and engineered to allow the maximum capacity to be realized. If not at the opening, then at a future date. So what they say, okay, you don't ensure that everything is done at the opening stage itself. Once you open it, then you can go on improving upon it. So at least open for, let us say, 100 kilometers or 200 kilometers, then you can improve it. So don't say I want 500 kilometer at so much cost and I don't have money for it. At least do it for a lesser distance or lesser length, spend so much. Right. So what are the factors to be considered? One is when you design high speed, what are the factors to be considered? One is line capacity, the number of trains per hour. So how many trains you are going to run? 30 trains, 40 trains, 20 trains. Then headway. What will be the gap between the two trains? How closer will those two trains follow? So that also depends on that. Also, you'll have to design based on that. How many trains can be run will also depend on the infrastructure, the power available, because it's all electrified. As you run faster, your motor or generator, whatever is there in the power engine, it has to run faster. It will draw more power. And more power means your OHE or traction system should be able to deliver that more power. And more power means equipments will not be costly. And equipments will have to be maintained correctly. It will be costly. It will be heavy, transported, erected, whatever, all the other factors that are associated. Then maximum line speed, you have to specify how much will be the line speed. The station spacing. So do you want any stations from A to B? Suppose there is a high speed line between A to B. Do you want any stations? Yes, a lot of people will say yes, we need stations. Why? For people to board and reboard and all that. Then how the terminal designs will be there, the terminal station. How soon can this train come back for the second operation? Once from A to B it goes, then how soon it can return back from B to A. Then gradients. So how will the track be laid? Is it on falling gradient, or is it a rising gradient, or is it a level gradient? So that is something. And then railway control and signaling system. So all this, based on this only, you will be deciding at what speed you will be running and what are the infrastructure that you will be providing for this high speed line. Then on top of that, after that will come this operating conditions. Now operations means the train stoppage, the train starting, all that. So dwell times at station. Now dwell time in the sense, how long will the train stop at that particular station? Is it for 1 minute? Is it for 2 minutes? Is it for 10 minutes? Is it for 20 minutes? Whatever it is. So this will also affect your headway and your journey time, running time, everything will get affected. Then terminal operations. So how soon it can come back. Then allowances for speed restriction. And recovery margins, it will also be affected. So I hope everyone is aware of what is recovery margin. So recovery margin means if the train is getting delayed, normally if you are a bit delayed to the office, what you do, you try to increase your speed of your vehicle to see that you reach your destination faster because you're already late. Is it a good method? Is it a good practice? It is not a good practice, because in your urgency to reach your office in time, you may cause a road accident, or you may get injured, or the vehicle may break down, whatever happens. So there will be some recovery margins. So normally what we say, if you are traveling in a train and the train is getting late by 1 hour, but to somebody who is in the destination waiting for you, you say that train may make up and may come 40 minutes late or 50 minutes late. This is what you call as recovery margin. You expect that at some portion where the train can speed or increase the speed, the driver will do it and will reach his destination 40 minutes late instead of 1 hour late. So recovery margin. Although we are looking at high speed lines, these conditions apply to all railways regardless of the top speed of the fastest train. Now this is some operational data with regard to HS2, the high speed train in UK. The train top speed was designed at 360 km per hour. That's around 100 meters per second. So 360 kilometers per hour. Train length 400 meters. So it's not like our trains 26 bogie or 24 bogies or good. So it is 400 meters. Average acceleration 0.3 meters per second square. It's a straight line calculation. Deceleration 0.5 meters per second square, straight line. And the service break distance now 110 kilometers. So it says if the train will need to stop 10 kilometers ahead, bring its speed to 0, then it will need 10 kilometers. The brake should be applied 10 kilometers before it so that it is able to stop. Now, why this is important? This is important if you are placing a station. Suppose the distance is around 300 kilometers. At 100 kilometers, you got a station. Now, if the train will have to stop at that 100 kilometer, it has to start applying its brake right from 90 kilometer onwards. So 90 to 100, it will be slowly deaccelerating and it will come to a stop at 100 kilometer. So during this 10 kilometers, the speed of the train will be deaccelerating. There is a buffer zone of 300 meters for automatic train protection. Driver's reaction time is given as 8 seconds. And ATP response time, automatic train protection, whatever is there, including the interlocking, is given as 8 seconds. And turnout operation is 10 seconds. Now, I think as a PWI permanent way, you may be interested in this turnout operation. What is this point operation and how so point operation, it says lock to lock time. So first, whatever the position of the point, it will get unlocked. Then it will operate to normal or reverse, and then it will get relocked. So all this should be done within 10 seconds. So this is how is some parameters with regard to HS2. Hope it is making sense and it is clear. Any questions so far? No. Now HS2 proposal was 18 trains per hour. There are a few assumptions. The route is flat. It has a top speed limit of 360 km per hour and operates electrical multiple units to already those well-known French, German and Japanese high speed. A speed of 360 km per hour is assumed since this is UK's HS2 chosen speed limit for a startup timetable, but below its 400 km per hour civil design limit. So the design is suitable for 400 kilometers, but for all theoretical calculations, we are going to take it as 360 km. A top speed of 300 km per hour might be more suited to the comparatively short distance of full speed running on HS2. So even though we are designing for 360, we consider that it will be whatever we design with all the practical considerations and theoretical assumptions, at least it will be suitable for 300 km per hour. Acceleration being constrained at the upper end of the speed range by the power available, modern electric train acceleration shows a broadly parabolic curve, which generally starts to fall more significantly from its maximum of about 30% of the top speed. And so these are certain information, of course, all this is the published HS2 documentation. You can just have a look into it. This suggests that up to 165 km per hour, the acceleration will be 0.21 meters per second square. After that, it falls to 0.14 per second square. So it cannot go on continuously accelerating at the same range or the same rate. So up to 165, it is 0.21. After that, it falls to 0.14. And this all compared to latest Japanese Shinkansen and other trains. The reference train, now, so this is a bit important. What it says is the reference train will take 333 seconds, that is 5.55 minutes, over 16.67 kilometers to reach its top speed of 360. So suppose it is going to stop at a particular station, and from the station it is going to start from zero. It is going to start from zero. So to reach its top speed, it has to travel 16.67 kilometers. Then only it will be reaching its top speed of 360. That means a journey time of 5.55 minutes. So if you are going to introduce a station, the speed of the train, the calculations will all come down. You cannot have exactly 360 because it has to, first of all, it has to break 10 kilometers away to bring the train to a stop at that particular station. After that, whatever the stopping time, 2 minutes or 3 minutes, after that it will leave that particular station and it has to travel at least 16.67 kilometers to reach once again its normal speed of 360. So these are actually very useful calculations if you are designing any high-speed railway. But more importantly, these are factors. So this can depend on the type of train. This can depend on the type of terrain. This can depend on the rules of that country, whatever it is. But all these factors you will need to take into consideration. And just somebody says why it is taking 5 years for bullet train, or why it is not being done within 2 years or 3 years. All that is a lot of thinking goes behind it. A lot of planning goes behind it. And a lot of expenditure also goes beyond it. It's not that you can do it in a day or two. Okay, so a few factors are important. What is the deacceleration rate? What is the acceleration rate? What is the speed? And do we need stations? Do we need one station? Do we need two stations? Do we need three stations? And if there is a station, then there must be a loop line. And if there is a loop line, there should be a point operation. And then where should be this point be? All that is a lot of thought. So braking, like acceleration, a train's deacceleration curve forms a parabolic shape, but that what the steepens at the lower end of the range. Again, a straight line approach is necessary to obtain a simple view on the effect on capacity. The braking rate adopted by HS2 is 0.7% G. Is not based on the current data currently available, sustainable at the higher speed on the of the speed range. So different calculations are there, different assumptions are there. This is only just a small article which I thought I can explain to you. Acceleration also, it says, being constrained at the upper end of the speed range by the power available, modern electric train acceleration shows a parabolic curve that starts to fall most significantly from its maximum at about 30% of the top speed. So this suggests that up to 165 km per hour, the acceleration will be 0.21, and above that level it is 0.14. Okay. Like acceleration, it trains deacceleration curve also. So this is your deacceleration curve, 360 to 300. So if it is traveling at 360 to come to 300, it is going to be deaccelerating at 0.49 meters. 300 to 230, it is going to deaccelerate at 0.52 meters. And 230 to 0, it is going to come at 0.60 meters. So this gives a braking distance of around 9270 meters. That's about 10 kilometers. That's what we discussed earlier. So 10 kilometers before the station itself, the train should start braking. Then only it can stop at the station. So if you think of all this, preferably you will say, I don't want any station. But if there is no station, then people will have only end-to-end travel without much benefit. So you will need stations, but you will have to plan it accordingly. Whatever is all this about braking, in consideration of in considering the train braking, it should be remembered it is the most difficult part of train operation. Any speed over 100 kilometers per hour, the driver must commence braking for a stop at a point from where the final stopping location is not visible. He is still not seeing the station, whereas normally if you travel at 30, 40 and 50, when the driver applies the brake, he is able to see the station and says, okay, 1 kilometer away, I'll be stopping. But here when he is commencing the braking, he is not even able to see the station. If line side or cab indication of the braking commencement points are not provided, the driver has to learn them from training. The braking commencement point will usually be conservative, with allowances for variation in weather, visibility condition, individual train performance, and individual driver performance. Many railways in UK nowadays insist on a defensive driving approach to reduce the risk of signal overruns, and some operators advise a platform entry of under 32 km per hour. So all this is how you can calculate and come down to a conclusion about how many trains per hour you can run, what is the theoretical speed, what is the practical speed. Okay, right. Another point is same. To consider for train braking is the need to reduce the rate at the lower end of the speed range in order to allow accurate positioning and to create a comfortable station stop for passengers, many who could be on their feet preparing to alight. Now this is something that you need to take care. Persons already who want to get down at that station, they will be picking up their luggage and they will be coming near to the entrance or exit of that coach. So if you are braking suddenly, then they will have a very severe fall. So you should be coming gradually and stopping at that particular station. So this provides an allowance of 730 meters for comfort and positioning. So 730 meter, you should be going at a comfortable speed so that persons are able to get down, pick up their luggage from the luggage rack, and then move towards the entrance of the coach to get down. Then we are looking at train separation. The fundamental objective of any train control system is safe and efficient train operation. To prevent collisions, trains must be kept apart, and if they are moving on the same track, there must be enough space between them to allow the second train to stop when the first train stops. This is often referred to as safe braking distance, and it forms a substantial part of train separation, which increases with speed. So for example, we already know that the train full speed braking is 10 kilometers. We need to assume there will be modern train control system. So no more our signaling. It will be all modern train control system with ETCS and ERTMS that monitors the train speed continuously and which will apply the brake if the driver fails to when the safe distance ahead is reduced. Appropriate indications will be provided in the cab. For safe train separation at line speed, the signaling system requires a braking distance of 10 kilometers plus contingency of a buffer zone between two trains moving at full speed. So the buffer zone has been suggested at 300 meters. Perhaps this could be regarded as excessive, but at 360 kilometers, it is only 3 seconds. So this is how the trains will need to be separated apart, 10 kilometers plus 300 meters. There is also a consideration of a train being stopped at the tunnel and the effect on smoke control airflow if trains are positioned too close together. There must also be an allowance for both the driver reaction and signaling response. So signaling, whatever signaling you are going to give, ETCS or ERTMS, that will also take some time to let the driver know. So all that timing also will match and the train will be run based on that information which the driver receives. So these figures vary from source to source, but one offer is 8 seconds for driver reaction and further 8 seconds for equipment response. So this adds a further 1600 meters to the train separation time, and including the train length of 400 meters and an additional time of 10 seconds for the turnout operation. The total separation distance between the two trains should be 12.3 kilometers. If two trains both running at 360 kilometers were following each other, they would be 123 seconds apart. This is what is called as technical headway. So at full speed, signaling headway, sometimes referred as technical headway, is 123 seconds. Based on all this calculation, length of the train, braking distance required, safe distance required, acceleration, everything. The 123 seconds, you can have the train. So that means a capacity of 29.27 trains per hour. However, there are a number of other issues that will be discussed further as we go. When routes diverge, there is a need for turnout. Then diverged or merging routes of the main line at turnout must be negotiated at reduced speed and the actual speed depending on the turnout design. So as a PWA, you may be interested to know what sort of turnout is provided, what sort of speed over the turnout, because every turnout based on the curvature will have to control the speed. The train speed will have to be controlled to ensure safe passage over the turnout without any derailment and without any accident. A maximum diverging speed of 230 kilometers per hour. So nowadays we have got turnouts with, I don't know how costly it is, but you can travel at 230 kilometers per hour on the turnout with what sort of drive it has and what sort of machines are connected, what sort of detection, all that is different. Maintenance of such necessarily high machined switch rails and a large number of point motors will need to be carefully considered. So if you're having a turnout which is having a speed of 230 kilometers per hour, then signaling is going to be very tough. You'll need more number of point motors and you will need to maintain it. Switch rail and all that should be correctly machined with correct friction to ensure that the turnouts are operated. Then imposing a speed restriction for a diverging train from 360 to 230, which will affect the following train if this has to pass the junction on the main route at 360. So what needs to happen? A train traveling at 360 will need to reduce to 230 because it's going over a turnout, and this turnout further is leading to a station platform. So this is going to reduce the headway between the two trains, sorry, increase the headway because the train is now going to pass this junction at 230 and the other train which is going to come at 360. So if it continues to run at full speed, it will violate its safe braking distance as it will close on the slow train moving ahead. To avoid this, the distance between it and the slow train must be increased. So this amounts to 22 seconds, which will increase the headway to 145 seconds. So earlier we said 123, now it has increased to 145, equivalent to 24.8 trains per hour. Earlier we said quite high, 29.27. So now we have reduced it to 24.8. So similarly, there are a lot of other calculations. Finally, say it should be high-speed turnouts are designed for 200 kilometers of operation. Finally, the diverging headway becomes 121 seconds. For a driver, the ability to vary braking between 0.5 and 0.687 is very slight in terms of control capability and therefore left without additional technical support. Throughout the railway, it will rely largely on the driver's skill. This is not an efficient solution and it points to the need of some degree of automation. In addition, this level of variation is less than required by bad weather, which may induce addition values as low as 0.3 meters per second square without a robust technical solution. So now what we say is the turnout speed is 230. As you go into this third paragraph, the turnout speed is 230 and the turnout will need to be located at 4.1 kilometer in rear of the station. 4.1 kilometer, the turnout will start. And then in 4.1 kilometer, the loop line will be running. And in a similar manner at the exit end also, if you assume 4.1, so the loop line itself may be about 15 to 20 kilometers long. So why it is needed? Because the train will need to brake from 230 kilometer, which it was traveling over the turnout and come to a stop at the station platform. 230 to 0. So it is going to take 4.1 kilometers based on its deacceleration rate. Ideally, from a headway perspective, this will be at the highest speed possible at 230. So this will locate the turnout at 4.132 meter in rear of the station in order for the train to follow a natural braking curve from full speed to a stop in the correct position in the platform berth. So hope it does make sense. It is not very easy to design high speed. Lot of thinking goes beyond it. Lot of planning goes behind it. And lot of expenditure also, because first of all, high speed turnouts, then separate layout of track, then signaling ETCS or ERTMS, and then your overhead electrification, whatever you provide, booster transformers or auto transformers or 2 into 25 kilowatt, whatever it is. All that is going to cost, and it's going to cost a lot of money. So this is how it's further discussed. The acceleration after leaving the platform. So if once it starts leaving the platform after waiting at the station, it goes at 0.3 meters per second square, requiring that the converging turnout for the 230 kilometers is possible at 6.8 kilometer from the station. So this turnout has started at around 4.1 kilometer from the station. After that, there is a station length of maybe 600 meters or 400 meters. After that, for 6.8 kilometers, it is still accelerating, and only when it passes 6.8 kilometers from its start of acceleration, it is going to reach its full speed. To better the acceleration available at lower speed, it will reduce, but even if the train arrives at the converging turnout at the exact time allowed by the movement authority, it will still further require 120 seconds covering 10 kilometers. So this will add another 21 seconds to its headway. So the average headway will now increase by 46 seconds. And all that, if you come to its final, the thing is, it becomes very low. So these timings will only be matched if the departure of the stopping train is timed to match the minimum converging movement allowed by the train control system. However, battle-hardened operators will know that station stop timings are notoriously difficult to predict. I hope everybody is understanding, because you can't predict how much time will the train stop at a particular station. It is not a metro train, it is a mainline railway, and it is a high-speed train traveling between two important junctions. So you cannot say that train will start within 2 minutes, or you cannot say the train will start within 3 minutes, because number of people may get down. Number of people will need to board. They have to find their seats before the train starts. So you will not be able to predict your dwell time. If you go here, yeah, right. Unfortunately, a converging scenario is not. So this is some study which was done by Arup and Hunyadi. The result is broadly similar to other studies since it assumes the same or similar train accelerating and braking performance. So what does arise from these variations is the need for a whole system model that takes into account the whole range of dynamic speed curves, allowances for train positioning and comfort, distance between stations turnout, relationship between station dwell time, train starting time, and passing of non-stopping trains. So an high-speed study itself is difficult, and more so because all these parameters are you are not aware of. So hope so far it has been good, interesting. If you have any questions, please put it in the chat box, or you can ask me later also. Right. Now we are looking into high-speed signaling now. The challenging and yet vital aspect of ensuring safety and efficiency in high-speed rail operation is mastering the synchronization between high-speed trains and signal timing. So whatever communication, whatever cab signaling you give, the driver should be immediately knowing it, so that he is able to take necessary action to either accelerate or deaccelerate or bring his train to a stop. There cannot be any delay. You cannot say that I will advise the driver after 2 seconds, because in 2 seconds the driver would have continuously sped and passed about 700 meters or 800 meters maybe. So whatever signals you give, synchronization, it means it should be properly timed and information should be given to the driver correctly. So normally even in your house or even in your office, you think internet is slow. Now if the driver gets a slow information about the signaling, then the train control is not possible. The rapid speeds at which these trains operate introduce unique challenges such as Doppler shift and changes in signal level caused by the movement within coverage beams. Now, even if you travel on the train with your mobile radio, you find that in some places you are not able to get the coverage. In the same way, if the driver is not able to get a coverage when he is operating the train and he loses the signaling information, then it becomes totally unsafe. So to overcome these challenges, specific synchronization signals in 5G network rail NR networks on belled out timing, whatever is the timing, I think more telecommunication will be able to explain, and satellite communication is employed. The synchronization of signal timing is crucial in ensuring safe and reliable operation, especially in high-speed environment where quick decision is imperative. And in high-speed rail signaling, every millisecond counts. Efficient high-speed internet service and linear cell-based radio or fiber systems are used to achieve millisecond accuracy in signaling system for high-speed rail. The, yeah, the level or precision improves safety and also enhances the operational efficiency. I think how much time? 20 minutes more? Yeah, I think 15 minutes. Okay. Right. So let me go a bit fast. These slides are all self-explanatory. You can just have a read. Discrepancies in signal timing for high-speed trains schedule may result in inaccuracies in timetables. So if the train is getting delayed by a minute or two, the second train which is following also will get delayed, and the third train will get more delayed. So all this is going to throw the planning out of schedule. So it's very, very important. High-speed trains, full automatic signaling, and without any delay in the communication to the driver about how the train should be controlled. Very, very important. So it is not that I will give 1 minute late or 2 minutes late. That's not acceptable, because any delay to this train is going to affect the trains in sequence, and the whole schedule will go haywire. So to coordinate cruise control strategy for the movement of multiple high-speed trains. So just have a look into it. Now, power supply and distribution system. This is something I just wanted to tell you. An upgraded power supply system and distribution system is a necessity for supporting the increased demand of high-speed rail signaling. So this is where you come traction interface. So what sort of traction, what sort of arrangements? Because high power means more current, and more current means more current to be generated, more current to be transmitted by use of proper cabling, and more current will be returning back to the substation. And if you are all aware, there will be some electromagnetic induction because of the return current on the signaling and telecommunication system. And more return current means more chances of electromagnetic interference. And that should not happen. So you need to take better precautions and protection. So this is what? So traction power supply system, signaling power supply also you will need more. Power sources, distribution network, and electrical loads, all of them will increase because of high-speed rail. High-speed rail signaling generally employs alternate current for power distribution, whereas traditional rail signaling in the UK has relied on two-wire 650-volt AC distribution system. So signaling power supply is on 650 volt, whereas that main load, the traction load, is on AC. And along with that, essential power backup system required for high-speed signaling include you need to provide UPS system so that any power failure should not affect system delay or signal delay and all that. So you will need to provide UPS systems, and advanced signaling system implementation at high speed will bring a myriad of economic and operational impacts, which will include enhanced line capacity, incorporating extra balances between main and distant to convey infill or in transitioning, improved reliability, and reduced need for line side equipment. So line side equipment will be reduced because you don't have any line side signals now. There are no location boxes, there are no controlling relays and all that. Everything will be cab signaling with the direct information to the driver with proper communication without any delay, right? So this is something that you can just read. Now this is something which may be interested to you. Although most of the current railway track are still on traditional ballasted type, recent applications tend more and more towards non-ballasted. So the major advantage of slab track. Now this is something that I just wanted to show you the figure. Hope you are able to see the figure. This is conventional ballasted track, and this is your slab track. So being PWI from PWI discipline, you all will be aware of what are the advantages of slab track and what are the disadvantages of ballasted track. So for high speed signaling, which is preferable? Anyone?
Slab track.
Slab track. Ballastless, correct. Ballastless slab track. Why? Because the ballast will become powder due to the high weight of the train, passage of train, vibrations and all that, the ballast will become powder. Whereas slab track is more beneficial. Which is more costly to install?
Slab track.
Slab track, exactly.
The last slab track.
Correct, slab track. So with the grow, this is something that I wanted to tell you. The general problem which occurs with the ballasted track is a slow deterioration of the ballast material due to traffic loading. Ballast consists of packed loose granular material of which the grains wander, wear and break up, causing increasing geometrical unevenness and clogging of the ballast bed by fine particles which cause drainage problem. Therefore, regular maintenance is time after time needed to restore the track alignment. So if you are using ballasted track, you need regular maintenance, you need regular cleaning of the ballast, you need regular replacement of that ballast. So it is more advantageous to go for slab track. Now we are looking at switch type also. Some rails still use switch blades made of standard rails. Figure shows the cross section for such a turnout. So now this is how is the turnout. Switch rail, hope you are able to see. So switch rail with integrated hydraulic setting and locking. So this is a switch rail with hydraulic internal only. There is nothing connected outside. It is internal. So this switch will move here or there. And this is your motor operated outside. Modern electrical point machine. So these are two different types of switches which are used in high speed. So figure shows a new integrated hydraulic switch and locking system. Here the locking system is integrated in the hydraulic setting cylinder. No lubrication or maintenance is required. The principle of integrated locking and switching machine enables the blades to move sequentially, so less power is needed at the same time. Okay, so these are different types of point machine. Now, vehicle reaction. Despite vehicle running stability, wheel and rail forces and car body acceleration at high speeds, they are confined to acceptable limit. As far as track is concerned, these vehicle reactions can be influenced by track geometry. In addition to quasi-static components which occur in curves, the response component is also dynamic part. So what they say is that the track should be suitable for high speed. The track should be designed for high speed so that the vehicle has got proper stability and does not fall either inward or outward, and also gives a riding comfort to the passengers who are traveling in the train. So all that depends on the track only. Signaling is okay. Signaling will tell you if the section is safe for running and no other train is there and the points are correctly set, route is correctly set. But what is more important is track, because the train is going to travel on the track. If there is any defect on the track, the train may tilt, the train may fall down, derailment, or it may have an accident, or persons who are sitting inside may feel discomfort due to the vibrations and jerks and whatnot. So as far as PWI is concerned, track layout is one of the most important aspect of, right. So now this is some special, it is called a geosynthetics. That means you need to examine the ground also. Before you lay the track for high speed lines, you need to examine the ground and see whether the ground can withstand such weight, pressure, and the speed of whatever it is. So what we will go here. So using vertical drains, this is also something I thought let me add. Then physical and chemical stabilization, several remedial measures are available to strengthen the subgrade materials. The common hydraulic binding agent is lime. In particular, for stabilization of soft clay formation, using lime can substantially increase the stability and load bearing capacity and decrease permeability of the subgrade. Now this is something I just wanted to show you. So rails, fastening systems, sleeper, ballast, sub-ballast, and these are certain supporting pillars so that it is able to withstand the train vibration and able to withstand the track stability also. So this is one method. Column pattern to improve the railway formation performance. And then I just wanted to tell you about benefits of employing slab track and disadvantages of slab track. This is also there. So reduction of structure height, increased service life, high lateral track resistance, great precision of track geometry, elimination of churning of ballast particles at high speeds. Disadvantages will be high construction cost, large alterations in track position and super elevation, adaptability to large displacements in the embankment is relatively small, and in case of derailment, repair work will take more time and effort. So advantage and disadvantage of slab track. And now finally, some benefits of implementation of high speed rail. It can be summarized as follows: reduction in carbon emission, increasing travel punctuality, offering more comfort than airlines due to larger seats for the same ticket price, more doors to exit for exit and entrance, quieter cabins, and no strict luggage restrictions. So this is one of the advantage of high speed. Contributing in development of regional areas, improving the land value along the demand corridors due to increased accessibility, increasing desirability of the country as a tourist destination and as a host for major world events, reducing air pollution, vehicle accidents, and traffic. So this is what is the whole gist of this presentation. There are a few slides which I had to jump over, but I'll be sharing this so you can just have a look. Okay. Right. So keep your eyes and ears open to hear more on the subject as more and more advancement takes place. Sometimes maybe 2 years down the line, 3 years down the line, everything has changed. No more signaling. Maybe track also, they will all come to slab track with all the proper foundations and designs and all. So more and more advancement is taking place, at least in this high speed rail. Different countries and different policies and different standards and different principles. Okay, right. So before I share this presentation, I'll be sending it to Sisira to share it in the group. Any questions? Anything you all want to ask?
So first of all, sir, thank you, sir, for such an informative session, and it was really descriptive. Coming from a track design background, it was really an eye opener for me. At least some of the things that you explained about operational features for high speed, that was definitely an eye opener, and it forced us to look at the bigger picture while we are designing our tracks or something. What are the other features that we need to take a look at? What are the other factors that will affect our design and other things? So thank you, sir, for that presentation. And then we'll move on to the questions. We have already some questions in our chat box, but before that, Srinagesh, sir, do you want to add something? And also, I think you have a question.
I don't think I have anything to add in sir's presentation because it was very, very crystal clear. It was really such that nobody can ask any doubt if he reads and really goes through the presentation. Thank you, sir. Thank you for that. And my question is, sir, that Shinkansen started way back in 1964 and TGV started maybe 10 years or 12 years later. With the speed of 210 and 300 kilometers per hour, and still how they are maintaining the same track and advancing the signaling system, keeping the same track in the same position.
No, track can remain. Track can remain because track has got the speed limitation, but the signaling system has now changed. Now it is no more color light signal and all that. We are coming into ETCS with the different levels and cab signaling and all that. So as you say, the track is still the same. So it is earlier what was designed for 300 is now still 300 only. They have not increased it. But signaling systems have changed. More number of trains are being run, and other high speed lines. Now suppose if you take bullet train now, which is what is being planned between Mumbai and Ahmedabad. So you now having analyzed this HS2, the way the design is progressing, I'm not very, what you say, I'm not very panicking about why it has taken 3 years or 4 years to see that it is just commencing, or because it cannot run on the same track. The track should be different. First of all, it cannot run on ballast track. It should be slab track. And to lay the slab track, you will need pillars, and pillars will need construction. So just like a metro construction, it will take years and years and years. Finally, you would land up, and then with the different stations. So how many stations you want, how many loop lines you want, how many main lines you want, all that. It will take a good amount of planning and good amount of execution. And I don't think anything is will be operative at least for the next 5 to 6 years, because it has been planned in 2020 or 2018, I think. But at least 2030, I expect to see the first train if I am alive. Yeah. Okay. Thank you. Yeah. Any other?
Yeah, sir. So we have some questions in the chat box, sir. First question is from Ramoji. So he's asking, where is the speed of 230 miles per hour on turnout used in UK?
No, not yet. Planned, designed, and planned. So not yet, but designed and planned. That is, I think you should go to that particular point, layout manufacturer, COG, Fire, or somebody is a name. So that is already there in the slide. So once you share the slide, you'll come to know it. So they will give you details, but they are still constructing. But 230 is already there. It is there. It's being designed 230 kilometer on the turnout with whatever slim radius and switch rail and whatever the length of the turnout, all that. Yes, they are designing it.
Thank you, Ramoji, for your question. So we have another question from you, Heng Lee, and for high question is for high speed signaling, is the train direction done via balises or axle counters?
No, it is done by balises. Axle counters also will fail after a certain speed. Balises only will tell you the correct direction.
So I hope your question is answered, Lee. If you want to add something or okay, yeah, we got to thank you also. So moving on to the next question, considering traction power, which one is more efficient for high-speed rail, 25 kV or AC or 2 into 25 kV alternating current system AC system? So this question is from Raman Kumar.
Okay, but first Raman Kumar should tell me what does he understand with this 2 into 25? What does it mean?
Yeah, Raman, I think if you're still in the
Yeah,
meeting, you can
hi.
unmute yourself. Yeah, go ahead.
Yes. Hi.
Yeah,
Yeah, 25 kV in 25 kV. Is it there is a indicative feeder is also provided in
correct,
that?
correct. So now we go for 2 into 25 only. The reason being that if you are going only with the 25 kV, because of more power, you will be drawing more and more current, and more current means that the transmission conductors, cables, fusing, and return conductor, return everything will be more expensive. By going into 2 into 25, your voltage is 50 kilovolts. To generate the same power, you will need less current, going by the Ohm's law formula. So that is the advantage of going into 2 into 25. So we use a booster transformer or auto transformer, and we go
Yeah.
into 2 into 25 to ensure that the current, the return current is reduced and it's kept within limits. Voltage is more. To give the same power, you need less current. That is under the same principle.
Yeah.
So we,
Okay. Thank
yeah,
you. Thank you very
yeah.
much.
And if you do have any doubts more on traction, then I got a very good book also. I can give you more explanation. But I thought here more PWI people will be interested. So I went into that ballast and slab track and all that. Yeah.
Yeah.
Okay.
Okay. Thank you. Thank
Fine.
you very much.
Fine.
Uh, so we have the next question from Anjan. Does the cab signaling system ETCS slash ERTMS eliminate insulation joints in rail?
Yes, it eliminates insulation joints in trail because there is no track circuit. There is no axle counter. It is all based on balances, and it's directly communicating to via satellite and gives the information about the train ahead or the train in rear with the distances and the gradient and the speed in which he has to travel. Everything is done by communication based only. So nothing is there on the track as an insulation joint. So if persons who are maintaining insulation joints, they'll be more happy if you do get high speed rails, because I know insulation joint is a pain to maintain and to install and efficiently manage.
So I hope Anjan, your question is answered. If not, you can unmute yourself and ask anything else you want. We'll move on to the next question. Next question is from Vikas. So do they use the transducers for CVTC signaling and for tracking the position of train in high speed route similar to metro?
Yes, they do. Of course, depends on the system, depends on the country where it is implemented, whatever system of signaling they use. They do use to track the train. So any more details on this, you can contact me separately.
So yeah, Vikas has also gotten his question answered, and so we don't have any more questions in the chat box. We have one raised hand from Lavi Khandelwal. Go ahead, unmute
Yes,
yourself
sir.
and please.
Thank you, Ankur.
Lavi,
Hello,
Lavi
sir.
Khandelwal,
Good
I will
afternoon.
not. Lavi Khandelwal, I will not answer because he is from signaling only.
So, just general
Yeah,
questions. So, easily we can say this is the ERTMS level 3. They run on the train on the ERTMS level 3 technology.
yeah, it is an ERTMS level 3, but it depends. Even see, high speed does not mean that everything, all trains will run at 300. You can run at 200 also. You can run at 250. You can run at 300. You can run at 400 also. So depends on the signaling system. So ERTMS, whatever the country adopts and whatever the country is able to adopt, in the sense it's going to be very, very costly. As I said, 76 million per kilometer for a double track in pounds in UK. It means the country दिवाला हो जाएगा दिवाला in the so that's why I think maybe Rishi Sunak has taken a decision to stop it right now and continue after he's winning the election, whatever it is, because it's very, very expensive. It's not very easy. First of all, land procurement, it is not something that you can do to an existing system. Now ETCS and
Mm-hmm.
all that you can implement in an existing system. You can remove the signaling, you can provide communication and all that. Here you cannot use anything of the existing system, neither the track nor the rail nor the signaling system
Mm-hmm.
nor the land, because everything is suitable only for 130 and 140 and 160. So if something has to be designed for 300, you should start right from scratch, including land procurement, including whatever other information. First of all, there will be a survey. The survey itself will take 6 months. The people who do the survey also will take their 10% or 30% commission. So it is all finally it is going to land in the government at some so many crores to do the survey. After that, procurement of materials, procurement of other, it's all very, very costly. It is something like you purchase a Rolls Royce, but still you cannot, it's not suitable for the same road on which you are traveling to the office daily. You have a Rolls Royce, but you cannot use it because the road speed is only 25 kilometer or 30 kilometers. So you have to drive it at 30 only. You cannot go at 100 or 160. What is the
Mm-hmm.
use of having a Rolls Royce or a Mercedes if you are not able to travel? So if you want a Mercedes from your home to your office, you should lay a new road, and only for you, you should lay it. Then you can travel on a Mercedes with good speed, 100 or
It will
100
be
or
too much
200.
costly.
Yeah. So that's what I say. It's going to be very expensive. And of course, they have planned it for years together. That's what I said. It will take another 5 years at least to see a bullet train from Mumbai to Ahmedabad with some
Okay.
halts in between. Yeah. Okay.
One,
Yeah.
Thank you, sir.
Yeah.
one
So
question
Nagesh,
I have,
Sri
sir.
Nagesh, sir, yeah, go ahead, sir.
Sir, this question is not related to high-speed signaling, but whenever there's a multidisciplinary project, our signaling team says that we are not doing the design, the supplier is doing the design. So what exactly does it mean?
We are not doing the design. You mean the
Yeah,
equipment design?
yeah. I mean, the supplier is. I mean, since I don't know much about signaling design, I just thought of
No, no.
asking this
See,
question.
if it is a design that is to be done at site, some wiring to be pulled out or some cables to be laid and all that, that is a signaling aspect. But
Okay.
if you are going into ERTMS and ETCS and such sort of advanced signaling, then we ourselves will be showing it in a black box and showing that input is coming and output is going. That's all.
Okay.
Yeah, that is what we say, suppliers information. So whoever is going to supply, suppose it may be Hitachi or it may be whatever it is. So Kyosan, now electronic interlocking in India, last of them are Hitachi and Kyosan. So they give the system hardware and all that, and they keep on programming it, and we only need to tell them where our external gears are connected so that it is properly wired and all that. So our design is only external. Internally we don't do anything. Internally is all suppliers duty only.
Okay,
Okay.
sir. Thank you.
Yeah. Okay. Fine. So thank you, Nagesh. I've seen you after a long time.
Yes, sir.
So
Thank you, sir.
have a good day, and we'll keep on meeting.
Yes.
Hmm?
So now
Sir,
that you have set a benchmark to us, we expect more and more presentation and more insights, sir.
Yeah. Yeah.
Because
Sure. Sure.
I think this was a really a good takeaway for us.
Yeah. Yeah.
It was
Sure. Sure.
very clear and crystal clear, sir. I think, as
Yeah.
you
Yeah.
said, if you read it, you will have no questions to ask.
Yeah.
Thank you, sir.
Exactly.
Thank you so much.
Yeah.
sir, we
Okay.
have one last question from
Yeah.
Shiva.
Sure.
He's asking, is there a speed restriction at platforms for trains which are not stopping at stations? This is regarding passenger safety aspect. Standing on platforms, what safety features are considered at station?
Yeah, exactly. I was showing in one of the slide that the speed on that of the train when it enters into the platform zone should not be more than 20 kilometers per hour. So that is a restriction they have imposed. This is more because of not to have any passenger injury, and also people may panic if they think there is a fast train which is approaching the station platform. And we have had many incidences on Indian railways where the trains have been, where the trains, Indian Railways, where the trains have been moving very fast on the platforms, and particularly when the main line is occupied with some other mail express train, the goods train also travels through the platform. And the goods train, an empty goods train, what will happen because of that empty bogies? Sometimes when it takes a turnout at a high speed, it falls off and it breaks the platform, and there is a derailment. So such cases have also occurred. So there are very clear instructions that no empty goods train should pass through the platform on Indian Railways. So like that, there are restrictions, there are safety information. So not more than 20 kilometers when the train is going to enter into the platform section is the restriction. Hmm. Okay. Yeah, right.
Yeah.
Okay. Thank you and cheers. Have a good day, and we'll see
Thank you, sir.
whenever
Thank you so much, sir.
whenever the next opportunity arises. Sure. Okay.
Yes,
Bye.
sir.
Thank you,
Okay.
sir.
Thank
Thank you,
you,
sir.
Thank
sir.
you,
Sure, sir.
Ankur.
Thank
Bye.
you, sir.
Bye.
Thank
Bye
you.
bye all.
Bye.
Thank
Yeah,
you.
Bye.
thank
Thank
you.
you.
Bye.
Thank you, sir.